So good afternoon to everybody. It is really a great pleasure to welcome Professor Enrique Zuazua. He is one of the most distinguished figures in mathematics. He holds the Alexander von Humboldt Professorship at Langen, Nuremberg, with appointments also in Madrid and Bilbao. He's author of more than 300 publications with a very high H index of 50. And he has supervised over 30 PhD students, and he received numerous prestigious awards, including the Euskadi Prize for Science and Technology, the Spanish National Julio Rey Pastor Prize, and 3 ELC Advanced Grants, and also the Simon William Thomas and Idalia Wright Prize.
Okay. And Professor Zuazua has traveled a long way to be with us today and to deliver this lecture on machine learning, mathematician's perspective. So please join me in giving him a very warm applause. Before to start, please minimize the use of smartphones during the lecture.
Thank you very much for the kind invitation and the presentation. Thank you, Monica, Julia, Carlo, for organizing this series of lectures. It's not my first time in Padua. I was here 10 years ago or so for an international workshop on hyperbolic conservation laws that I think was organized in particular by maybe Fabio Ancona. So I know this is a very large department and very prestigious one. We of course see often Padova in all activities related to mathematical analysis, applied mathematics, control theory in a very broad sense. So today, well, maybe the title is a bit ambitious, but it's an orientation of what I am aiming to do. It's just to try to analyze some aspects of machine learning and artificial perspective from precisely, my own say, atalaya, right? Do you have this word in Italian? Atalaya. I mean, the watching pedestal, right? So, from very far in a small corner of mathematics and applied mathematics, I was trained as a mathematical analyst in Paris 6, nowadays Sorbonne University, and then at that time we learned PDs, functional analysis for PDs, numerical analysis, and then we learned a little bit of control theory, and I developed a career doing analysis, numerics, control, also with some applications in view, like for instance aeronautics, which is one of the classical topics in which control theory finds one of the main fields of applications. And it was when getting to Erlangen back in September 2019 that I observed, Erlangen is a beautiful small town. It was founded by the French Huguenots when escaping from France. It's next to Nuremberg, and other than having the main campus of our university, Friedrich Alexander University, we have a very wealthy perimeter for technological transfer. We have the Fraunhofer Technological Institute, the most important antennas of the centers of Fraunhofer technological network is in Erlangen. In particular, they are very well known for the patent of MP3, right, for compressing sound. In town, we have Siemens, that of course they have a very important activity, in particular on building these big scanners for magnetic resonances, and therefore there is a very strong activity in imaging, image processing, in cooperation with our medical campus. We have the automotive company Schaeffler. We have also Adidas and Puma. Now, of course, they are interested in developing new materials and all kind of research related to biomechanics for obvious reasons. So, but then I observed that many of these companies were interacting very actively with our university, but most of them were very much interested in using tools in machine learning and artificial intelligence. And then this is when I said to my team, well, maybe we should make an effort to try to understand this, because probably all we know in a way or another is related to this. And then I will tell you how was more or less my journey, how we little by little we discovered a number of things, we understood a number of things, and well, I will present you this in a more or less non-linear manner from the perspective of what I have learned until now. Hopefully this will be accessible for most of the audience. I think anyone with a minimal background on analysis and applied mathematics, either mathematician, computer scientist or engineer, should be able to understand this. And then, as I was saying, claiming that this is a mathematician's perspective, this is too ambitious, because I think the field of machine learning and artificial intelligence is like an Amazonic forest, right? So it's a huge field, it's growing very rapidly every day. I mean, even in Twitter, you just follow the tweets about the most novel contributions to artificial intelligence and machine learning. There are several of them every day. Very agile, very smart, very innovative, very intuitive. And we mathematicians, we are a bit slower. We need more time to understand things deeper, to get into the principles. And this is, of course, something you can do from all fields. I mean, as an analyst, you can do that. As a computational mathematician, you can do that. You can do that as a control theorist, but also if you are a geometer or someone expert in approximation theory, algebra. I mean, all fields have a common intersection with machine learning and artificial intelligence. And my recommendation is always, I mean, don't try to read everything in the field. There is too much, but you can certainly from your own field try to penetrate, and build your own path to discover this very vibrant field, right? Okay, so the scientific context we all know. 4 or 5 years ago, or 3 years ago, I don't remember. I think 3-4 years ago, I didn't even know ChatGPT existed. It was we were taking a train with my colleague in one of the top experts in this area in Erlangen, Andy Maya. He's in the Department of Computer Science, and he's doing a lot precisely in this image processing in interaction with Siemens for biomedical applications, pattern recognition, employing not only mathematical classical tools, but also artificial intelligence. And I think he was the one in the train who told me about, well, listen, maybe you should give it a try, right? So soon after ChatGPT, we discovered DeepSeek. This is the Chinese version, which does sometimes better, sometimes worse, but it's free. Many people use it because it is free. And probably the breakthrough of DeepSeek was at least to claim that they were able to do essentially the same thing as ChatGPT, but using much less computational resources, right? And that was quite impressive because, well, I mean, of course, this is like when you are doing numerical analysis of PDEs, where you have two methods, well, maybe, classical finite elements of order 2, and the other one does hierarchy discontinuous, and then they will get similar results. You expect similar computational complexity, but here the claim was that DeepSeek needed much less resources to train the large language model that they were able to build. But this is somehow our daily life artificial intelligence reality nowadays. We all have it in our computer or in our pocket, and this has been a revolution, the same way it was a revolution 25 years ago, Google, or internet, say, 40 years ago, or personal computers more or less also at the same time, right? So probably those that have been here for a while will remember the first day that personal computers started to populate the desk of offices. I think this happened probably in the second half of the 80s, right? And then email became more popular, and in this way, the faxes were used less and less until eventually almost completely replaced, although in the official forms there is still a room to put the fax number. I don't even know what my fax number is, right? So, okay, very good. So this was a real revolution. Now we can use it for everything. We can translate text from one language to another. We can write a text and then ask to ChatGPT to make it a bit more formal or to correct typos, or to properly place all commas. I mean, there are many, many things you can do. You can even ask about links between different fields. You can ask ChatGPT, oh, can you explain me, please, the connections between machine learning and control theory or Fourier analysis? And ChatGPT, furthermore, is always extremely nice and supportive. It always starts saying, oh, that's a great question, right? Regardless of what you ask, that's a good question. And then immediately you will get a... of course, you have to be cautious, right? You have to double check the computations that it is providing, although very often it's correct. I don't know, you can ask ChatGPT, is the Fourier transform of this function, is it explicit? You don't recall. Or is the Laplace transform of this function, is it known? And you know, ChatGPT is able to do this. If you are satisfied by the answer, you can even ask, okay, put it in a LaTeX file, and then you can do it as maybe as an exercise in your master notes. You have to be careful though with bibliographical references, because very often it provides fake bibliographical references. And it's not easy to guess, because you ask for references in a given field, and then probably, you know, the title will be sound. The author or authors will be also people in the field. The journal will be also appropriate to the field. And maybe more or less the timing, it will fit more or less the time where this kind of research was being done. But then when you go to Math.CNET and you search for this paper, very often you realize this paper doesn't exist. Right? So ChatGPT has generative power. I mean, these tools, these large language models, by the way, we will discuss what large language model means, they have generative power. We all like it, right? So I don't use it much myself, but people that know how to do it, you can generate a new image every day with ChatGPT saying, okay, please produce the poster of a math conferences in mathematics and machine learning in Padova, by the river and next to the cathedral. And you will immediately get a new image generated. We all enjoy all this generative power. The problem is that this generative power is also used when you are asking for bibliographical references. And this is not what you want, right? You want real bibliographical references. You don't want ChatGPT to use its imagination to generate bibliographical references of papers that never existed. Okay? Very good. But anyhow, this is our pocket. You can ask, I don't know, what is, I didn't do, but what is the origin of the word Padua? So what is the origin of the name of the city? And then probably you will get some relevant information, very likely approximately true. Okay? Very good. This is the pocket artificial intelligence, but there is also the big artificial intelligence having a serious impact on science. And this was, made explicit in the Nobel Prizes that were awarded last year for chemistry, for the use of artificial intelligence for unfolding proteins. I mean, these are very complex geometrical problems related also to the classical key issue of the course of dimensionality that we will discuss later, something that was coined, introduced by Bellman in the probably late 50s or early 60s, when dealing with control problems. This is something that everyone knows here, right? So Bellman realized, well, if you want to control a dynamical system, it's not that difficult. You have to compute the value function, and the value function solves a Hamilton-Jacobi equation, which is a nonlinear PDE. But now the question is in how many dimensions. So it turns out that if you are dealing with the motion of a particle in 3D, so this is a three-dimensional particle, it's just a fly, right, evolving, right, or a tennis ball evolving, just 3 coordinates. The Hamilton-Jacobi equation is already in 3D. So assume now that we build a WhatsApp group of all attendees here. We are 40 people, right? If we want to track our state of mind or opinion about the mathematics of machine learning a long time, this will be a dynamical system of 40 dimensions in which we simply record either 0 or 1 for each person, right? So whether we like it or not, this will be a vector in the hypercube of dimension 40, and then the Hamilton-Jacobi equation, it will be a nonlinear PDE in dimension 40. Okay, then you go to the book, and you will see, all books in finite elements, they say dimension either 1, 2, or 3. And then there is time. So we are so far from 40. And our human intuition is totally lost, right? So we can understand 3 dimensions, right? The 3 special dimensions, spatial dimensions we understand. But for the time, we need the watch. Right? So we don't even master 4 dimensions properly. We need the watch for 4 dimensions. And our perception of the time is very elastic, is very nonlinear, right? To the point that for whoever is speaking, the lectures are always short. And for those that are listening, the talks are almost very long, right? Same talk, just depending on which side you are. Okay, so this was using artificial intelligence for untangling these geometric problems in high dimensions that we hardly can have an intuition about, and we fail to solve by using standard tools in applied math in which you can really write down a program in which you concatenate instructions because you really know how it has to be done. Right? So this is not one of those problems. Artificial intelligence was one of the keys, and the Nobel Prize in Physics to Geoffrey Hinton for his fundamental contributions, mathematical contributions, say, to this field of artificial intelligence and machine learning. Okay? Now, when you ask yourself, when did machine learning start? So when was the starting point of machine learning? It was when ChatGPT started. It was maybe before, when people in the 50s were already developing models inspired in neural networks. Maybe a bit before, when Turing started to develop the first computers, or maybe related to the emergence of information theory, maybe rather in the 30s, Shannon and so on. When can we say that machine learning started? Actually, I would say that machine learning started almost 2,500 years ago. Because Aristotle, in his book Symphonicus, he already claims that one of the main ambitions of humans should be to develop machines, to build machines, to create machines that will be able to do the work they used to do, so to make them free. And this is something we have really achieved very nicely. So I can talk here, I don't need to take care of the light, there is internet, there is video projection. If I go to the toilet, there will be water. If I go to the gas station, there will be gas. Everything has been made automatic. Many things have been made automatic, and this is why our society nowadays is very different to the one 100 years ago. Okay? So this has been a very long process, and in my view, artificial intelligence is just one further step in this ambition of making things automatic. So that now, if you have a text in Italian and you want to translate in English, you can of course do it yourself. But frankly, would you spend 2 hours writing translating a letter from Italian to English if you can just do it in 2 minutes with ChatGPT? Maybe not, right? And this applies to many. For instance, yesterday I had to submit a proceedings article online. I have done the revision many times. And this morning I said, let me ask to ChatGPT whether it's able to still find some typos. And indeed, there were still a few typos. I was not able to see them, they were still there. Some commas that I have missed, some point I was missing after a formula, some contradictory notations I was still using. Amazingly, that was done in just, I don't know, half a minute. something that would have taken maybe 2 more hours to make a new revision of these 20 pages. Okay? So this has been extremely successful, but we are just pursuing the program that Aristoteles formulated for us. Of course, probably one of the fields that in mathematics that has more contributed to this Aristoteles program is control theory. So I like very much this front page of a report that was published. There were at least 2 reports of SIAM, the Society for Industrial and Applied Mathematics of the US, that, as you know, operates very much as a global organization. Back in '88, there was a first report on the state of the art in control theory, and there was another one in 2003. You can download it online, although I'm not sure when you download the PDF you get the front page of the printed version. I like very much this front page because on it you recognize a number of devices and technological inventions that are very much related to control theory. So these are airplanes, of course. I think this is one of the first pictures of the Wright brothers for the first airplane. This is a modern airplane. Of course, networks in different configurations, network telecommunication. This is a biological cell. This is a robot. This is a microchip. This is what? Maybe some people don't even know what it is now. Do you know what it is? No. Young people don't even know what it is. So this is a thermostat, an old thermostat where you say, I want temperature to be 20, right? And then the heating and the air conditioning will do the job. There will be a sensor measuring the temperature. Whenever the temperature goes above 20, inject cool air conditioning. And whenever temperature goes below 20, you inject hotter heating, so to keep the temperature around 20. It will not be 20. It will not be exactly 20. It will be 20, something, 19,999. But of course, I mean, we are not able to feel that difference. Frankly, I cannot make the difference between 20 or 20,001. Okay? So then you will get a profile of temperature that is an oscillatory path around this constant steady state of 20 degrees chosen. This is the thermostat, and this is even older. So this is the governor. This was probably the main invention in the Industrial Revolution. This was the governor engine in order to keep the pressure on the steam engine of that constant. Of course, you need to keep pressure in the engine to be constant in order to realize a constant performance. If pressure increases too much, there is a risk of explosion. And of course, if the pressure is too low, the performance of the engine would be too low. And then the idea was later implemented in many other devices, like the gramophone. I mean, we all know that it's not very nice to listen to music played by a disc player where the velocity of rotation is non-constant, right? So you don't want the velocity of rotation to be stationary, to be oscillatory, you need it to be constant, and this is the kind of engine that is used. Also in the classical pressure cooking devices, how do you say in Italian? Pentola pressione, right? So, and probably you have seen that these all pressure cooking pots, they have a vertical axis with a small hole and sometimes an annulus, embedded in this axis. The idea being that when the pressure is very high, the axis rotates, the annulus goes up, this little hole, gets open, and then the steam goes away. This reduces the pressure inside. With this, the velocity of the axis goes down. With this, the annulus goes down, and this hole that was releasing, the steam is then closed, preserving the steam inside. Pressure goes up and down, and this was the invention, I think, of VAT. This is the so-called governor mechanism, and this has played a major role in the Industrial Revolution. I think it was Lord Maxwell, the same as for electromagnetism, who wrote the first article on this mechanism back in 1868, where he was analyzing the stability of these mechanisms using ordinary differential equations. Right? So basically, the remark he made is one of the fundamental ideas in control theory. He made the following observation, because he was trying to explain something that engineers observe, is that very often the performance of this mechanism was not commensurate to the effort they were putting on the design. Sometimes very rough mechanisms were performing very well, and then when they tried to do it in a very sophisticated manner, very fine materials, with a lot of articulation between the different segments, concatenated and so on, they were seeing a more unstable performance. And it was Lord Maxwell who indicated, listen, this is something you can already observe on the stability properties of the damped oscillator, right? And he was right. So if you take the classical harmonic oscillator with some damping coefficient D, right? Of course, the energy here is just the addition of the potential energy plus the kinetic energy. If you compute the time derivative, this is what you have, right? And you can easily prove that the energy goes to zero exponentially, because you can apply Lassalle's invariance principle using the energy as the Lyapunov function, and we are in the linear setting, so the decay has to be explicit. The question is, how does the decay rate depend on D? Of course, when you see this formula, our first intuition says, oh, the more you push with D, right, the better the decay will be. So our first reaction is monotonicity. Yes, but we know that not everything is monotonic in real life, right? So this is, for instance, what generates the bubbles in the stock market. People, or in the real estate. I don't know what the situation in Padova is, but in Spain we had a big crisis back in 2008 or so, because the prices were increasing and increasing and increasing, and this was stimulating, the fact that people were buying and buying and buying, because, of course, if this monotonic increases, you buy, because next day you are wealthier. Yeah, but nobody thought that probably there would be a maximum and then a big drop, right? So something like this happens here, and this was observed by Lord Maxwell when he said, listen, if you compute the eigenvalues of the corresponding characteristic polynomial, is this. So the lambda is minus d plus minus b squared minus 4 divided by 2, right? And when you check how the eigenvalues of this problem behave, you realize that there is a critical threshold which is d equal 2. And actually, when you then write how the amplitude of the damping impacts the decay rate, right, you see that this is saturated at d equal 2, right? So beyond d equal 2, you are in what is called the over-damping regime, meaning that you are damping the system more, but the performance of the system is not any better, right? And this was considered as a good explanation of what people have observed when building different versions of the governor regime. Of course, this idea of over-damping is the same as you encounter in machine learning when people talk about overfitting, right? So you have data, you try to learn, yes, but if you learn too much, you overfit, right? And this is actually an obstruction for later generalizing. And generalizing is something we expect from artificial intelligence, right? Because amazingly, these tools, these large language models we use, they work amazingly well. And the more you think, the more surprising it is, right? Because they told you, yeah, of course, ChatGPT has learned all the Wikipedia. Okay, well, assume, ChatGPT has learned all the Wikipedia in the sense we can imagine as a big, someone with a very big head, you know, reading all the Wikipedia and being able to memorize all the contents of the Wikipedia. Yet, when you ask for links in between different concepts, it's very fast on doing this, right? So you really expect it to generalize well. Generalizing well meaning that not only you are able to answer to the questions that you have learned about, but actually that you are able to answer to new questions that you didn't see before. And this is what precisely you expect from a mathematician, right? So either in an exam, it's the same, right? You learn how to do 50 integrals, but not to just to memorize how, you know, you compute these 50 specific primitives, but rather because once you master all these ideas of integration by parts, changing variables, and so on, then you are ready to tackle new integrals that you have never seen before. Okay? So overfilling, like overdumping, is about doing too much about a little corner without later developing capacity of facing new scenarios. Okay, so this was control theory back in 2003, right? At that time, people were not really talking yet about artificial intelligence. Nowadays, everyone is, of course, interested. There is this interesting paper by Alexander Fradkov, a professor in the Soviet Union. He makes this short, he has also a longer version of this article about the early history of machine learning, and there he explains how, when you look from close the mathematics of machine learning nowadays, you will discover that many of the ideas that are being employed nowadays are already well known. And this is true, right? So, I mean, the article, of course, is written from the perspective of someone educated in the Soviet Union, but he's right, that of course, when people have to deal with concepts as complexity, then you will use ideas of Kolmogorov, like Kolmogorov width. That many of the problems in artificial intelligence are related to optimal transport, Monge or Kantorovich, right? And that many of the problems of training the models of machine learning are related to classical control and optimization. So you will see, of course, key ideas like, Pontryagin maximum principle. Okay? Many years ago, we also wrote a paper on the history of control theory, more from a mathematical perspective. Again, at that time, we were not thinking on artificial intelligence, but well, you can see still some of these old concepts that are advocated by Fradkov. And now we are to this point where we say, well, we are mathematicians, so we are engineers working in this specific aspect of computational and applied mathematics in a very broad sense. And we would like to get interested to get involved in machine learning. So how can I do it? Well, basically, you have to build your own bridge, as I said. Artificial intelligence is like a new planet, right? So then you have to find your own, your own shuttle to bring you there. You have to build your own bridge from wherever your field of expertise is. And this was the bridge we fought, right? Maybe some of you have already seen this video. So here on the left you see a classical application of computational control. This is a joint article with Dong Man-Ko, who is now a professor in Seoul, back in Korea. To the left is control, and to the right, this is supervised learning, right? So hopefully it will help you. Okay, very good. So I tell you, well, the video to the left is control theory, and the video to the right is machine learning. But if I tell you so, maybe you believe it. But if you watch through these two videos, you see similar things, right? So what I see, both of them are particle evolving. In the video to the right, particles were just data that I needed to classify according to the labels. So these data were mixed initially, right? They were mixed, and then I succeeded to classify them according to the labels. the same students do when getting to campus. All the students get to campus, but then depending on whether they are in math, economics, or engineering, they go to different buildings. So somehow, on the right, we succeeded to build a deep neural network. And then I have here show you how this new deep neural network, layer by layer, evolves like a dynamical system so that data get to the corresponding destination according to the labels. Yellow with yellow, green with green, purple with purple. On the left, I said this is control theory. Well, why? Because actually there are 4 controls, are the 4 dogs in blue. So 4 dogs in blue. And then here I had a few hundreds of sheep. And these sheep were pushed by the action of the dogs to move from the original location here to the corresponding final location they didn't know about. Right? They didn't know about. You know, sheep were very happy here. You know, they were just resting over there. Dogs were very far away. And the task that was allocated to the dogs was to bring sheep from their original position here to the destination over there, to the shelter where they have to spend the night. So what do the dogs do? If you watch the video now, a posteriori, we solve this by writing a very large dimensional interaction particle system, in which the interaction between the different particles is asymmetric, because sheep like to be together, but they are frightened by the presence of the dog, so as soon as the dog approaches, sheep move away, and on the other hand, dogs like to be close to the sheep, they are attracted by the sheep. So this is a non-symmetric dynamical system of interacting particles, sheep with sheep, and sheep with dog, dog with sheep, hundreds of differential equations. So what we did was to solve an optimal control problem computationally, right? In which we said, well, the goal is that the blue dogs develop a motion strategy that will bring this red sheep to the corresponding destination. And when you see the video, what you see is that the dog starts dancing in a way that is a bit surprising the first time you see it. But when you read off a posteriori what the dogs have done, you realize that the dogs have built a diagonal corridor, right, along which sheep spontaneously move. Why? Because sheep simply at any time, they try to be located on the point that is the farthest away with respect to the position of the 4 dogs. Sheep are afraid of the proximity of the dogs, so wherever the collocation of the dogs is, the sheep try to be at the center of this polygon, right, that the dogs are generating. When the dogs move, this polygon moves, and then sheep trying to be at the center of this polygon in order to maximize the distance with respect to the 4 dogs, they spontaneously evolve in the destination, in a destination that they didn't know a priori. They just follow their intuition, their repulsion with respect to the proximity of the dogs. So you see, this is classical control theory, this is machine learning, but the 2 videos look the same. There is a big difference though from left to right. What is the main difference you observe from left to right? So here I could claim that these are sheep. I mean sheep of 3 different colors. But on the right, I observe that something is missing, right? There are no dogs. There are no controls. And this is why people will say, well, machine learning is not like in control theory, because in control theory, there is a state and then there is a control, and the control is chosen, right? Feedback or open loop or whatever, but the control is chosen so that the state gets to the destination. And it's in this way that you can send a rocket from Earth to the moon, right? Okay? The driver is the one that is operating the system, playing the role of the control. So here, there is no driver on the right, there is no control. But actually, when you check, you ask yourself how people built this dynamical system, time discrete dynamical system, that is able to take these data that were totally mixed, and the system was able to undo this knot and bring every particle to a different destination according to the label, to the color. When you look how this dynamical system has been computed, this has been used optimization techniques. Although in the context of machine learning, they call it training. So in this model, the controls are there, are the classical parameters on a neural network that have been pre-computed in an offline manner. And what you see here is just the deployment of one more application of classical open loop optimal control in this context applied to machine learning, where the terminology changes, but the ideas remain. And this is precisely what Frankov says in his paper. Okay, so this was the scientific context. Now, I would like to explain you a little bit of how it works and why it works. Right? So as a mathematician, probably these are the two more striking questions. And there are many, many technical problems one can consider. Many of them, of course, will be extremely complicated. But I think we all agree that as mathematicians, it is worth to make an effort to try to understand how it works and why it works. Okay? So how it works is this. This is just one slide. I mean, of course, this is very, very simplistic, but the idea is already there. Right? So what we do is the following. So first of all, we build a neural network. Well, what is a neural network? A neural network is just a graph, right? We all know a graph, just connected nodes in which that can be described through the connectivity matrix. Whenever you have a 0, it means that the node A is not connected to the node B, or the node I is not connected to the node J. And when the coefficient is very large, it means that that there is a lot of communication between these two nodes. This will be a linear graph. But we claim that this is a neural network. So a neural network is just, say, a graph in which every node is now set to be a neuron. But because it is a neuron, then as in biological, spy on human brain, this neuron can be either on or off. A classical concept also in control theory. In band control, the control can be on or off. So sometimes the most efficient control strategy is just do nothing and let, this is like, wait in the bus, you don't need to do anything. You just stand in the bus station and wait until the control comes, the bus comes. So this is band-off band control, okay? So you see a neural network therefore is a graph in which every node becomes a neuron and therefore can be either on or off. Meaning that when you are dealing with one of these neural networks, you can do basically two things. With one hand, you can tune the intensity of the communication between different nodes, and then with the other hand, you can decide which neurons are on and which neurons are off. And of course, you don't need to do it bang bang. I mean, you don't need to do 0 or 1. You can also say 20%, 30%. You can choose the intensity of activation of each neuron. Okay? Therefore, the model is non-linear. The graph is linear, but the fact that you are tuning on and off or choosing the intensity between 0 and 1 makes the model to be non-linear. So, but why do I consider this graph? Well, because this graph is basically the one in which every particle entering in the system, so this will be like a tube in which I place a particle. This could be one of those particles, yellow, green, and purple. I will place, a particle in the entrance of this tube. And when exiting the tube will say, according to the color, the particle should go either, yellow or purple or green. This is what I expect. The tube to become intelligent and be able to map every particle in a different destination according to the label. Okay? So the map that I am building, the function, the mathematical function I am building that maps every particle to a different region of the Euclidean space according to the color is not built in a static manner, it's not given by a formula, logarithm of the sinusoid of the square root of the Euclidean modulus of the vector, but is rather let evolve according to the dynamics indicated by this neural network, in which depth is horizontal, layer by layer, this point is passing through different gates, right? And width is the dimension, right? So depending then on the exercise I'm trying to solve, for instance, if I am dealing with points in 3D, probably there will be 3 neurons at the entrance, and if eventually I have to choose between -1 and 1, then at the end there will be just 1 neuron. But you see that, like in an accordion, right? You can choose the width and the depth of this neural network the way you wish, right? You can make it small and then shallow, just 1 layer, or you can make it very width or very narrow and then have 1 neuron many times, and then the neural network becomes big. There are many possible versions, okay? Anyhow, we fix the architecture somehow, the size and the complexity of the architecture has to be adapted to the ambition of the problem, right? So maybe if I have just to, I don't know, classify students in class according to the records in the different courses, I don't need such a big neural network. I'm dealing with 40 people. If I need to learn the Wikipedia, I mean the task is monumental, probably I will need a bigger neural network, okay? But, okay, from a mathematical perspective, we fix the architecture and the size of the neural network, and then the only thing I have to do is to choose with one hand the connectivity coefficients, and with the other the on-off in each neuron. So this becomes a finite dimensional problem in which I have to just determine the values of all these coefficients optimally. Of course, the number of coefficients grows very fast, right? And therefore, this is why it's very easy to face the course of dimensionality of these problems, because even in a neural network like this, there are already a few dozens of neurons, and for each of them I have to determine all the connectivity coefficients and whether it's on and off, and this makes the search space to be a very high dimensional Euclidean space, okay? But then, how do I do my choice of the optimal parameters? What do I optimize? Well, normally, what you do is you place yourself in the context of supervised learning. Supervised learning means, for instance, if you have to classify, I don't know, radiographies of the traumatologies, you have radiographies of many arms, and then you have to classify radiographies exhibiting some kind of fracture and non-fracture. 2 categories, right? So how do you do it? Well, if you are a very expert doctor, you can do it one by one. You watch, and then the doctor will immediately say, well, we can see indeed here a huge fracture or a micro fracture. This is fracture, this is healthy, this is non-fracture. The doctor can do it. But you want to build a machine that automatically does that. How do you do it? Well, you take a collection of, say, 100 radiographies where you have the labels. You have F for fracture and NF for non-fracture. And with this, you build a data set in which you have the image is X, and the label F or non-F is the Y. And then you try to build the neural network and the coefficients so that you match, for every of these, supervised data set you have of these available 100 radiographies with labels, you try to make sure that the input to output matches, the data you have. So you just minimize the loss function in which you are simply, penalizing the distance from every radiography in your 100 collection set. So capital N will be 100, and this will be just the gap between the exit of, this neural network on each radiography to the corresponding label. Of course, in order to avoid problems with coercivity and and the existence of a global minimizer for this problem, you will apply some, Tikhonov penalization in order to guarantee that the different parameters entering in this neural network that I will explain later, but basically are, the intensity of the connection and how much you do it active or not active in every neuron, they are penalized to guarantee coerciveness. And that's it. So when you watch this, you say, well, but this actually reminds what? What is the old tool in mathematical analysis that we all identify there? Well, this is basically least squares. This is what Legendre back in 1809 and Gauss, Legendre was 1805 and Gauss published his paper in 1809, although he claimed he was using it much before Legendre has published his paper in 1809. It doesn't matter, it's more than 200 years old. And we all know this, is least squares. And so what Legendre and Gauss said, this was already, I would say, a fundamental contribution in machine learning and artificial intelligence. At that time, they didn't think it that way, probably. But they were already, inaugurating this age in which, these large language models are built based on simply this training or optimization exercise to feed data. So for them, they wanted to feed a class of data, and they said, well, the merit is not really on building a code that passes through every point. You have a pen and paper, you can always do that. This is a nice, exercise, maybe to check how, your attention and your vision is performing. You can maybe try to do this exercise, but this doesn't have any prediction capacity. If you want to predict something, say about temperature or delays on the regional trains, instead of trying to build a path that passes through all these points, what you need to do rather is to build a simple path, for instance, a line, right, that will capture the essence of this cloud, and in this way will give you not a very precise answer, but yet a quite predictive, say, a priori guess of what's going to happen in the future. Of course, they were doing this by hand, no computer. So therefore, they were limited to consider very simple models like linear functions, in which the only thing you need to fit is the value of the parameters beta 0 and beta 1, right, for the linear function. But the idea was already there, right? So they were minimizing the gap between the label y and the anticipated value of the function f taken on the data xi. So input, output, input on the x-axis, output on the y-axis, a collection of points, xi, yy, a model, a linear function, and then try to minimize the sum or the average of all the residuals squared. This is already what you see in this, say, monster version being implemented in the context of neural networks. Of course, the difference is nowadays we can use computers in order to solve these giant optimization problems. Okay? But now, when you ask yourself how big these optimization problems they are, there is this web page, 3 Blue 1 Brown, where you can find very interesting videos about some of the main ideas and methodologies employed in artificial intelligence and large language model. There is one in which the architecture of ChatGPT-3, this is the ChatGPT-3, it's not the ChatGPT-4 or the ChatGPT-5 that we have in our pockets. And there the author describes Sanders, I think is the name. It's very well done. I actually use it very much also in my master because it's a very concise and impactful way of conveying some of the main ideas. You can do the math afterwards, right? He explains that in ChatGPT-3, in the 3 version, the number of parameters, so basically the dimension of the Euclidean space in which we are solving this optimization problem is of the order of 175 billion. So there are in ChatGPT 3, in ChatGPT 4 I think it was a trillion. So here are American billions, right? So billion means, 1 billion means 1,000 millions. So this is basically, ChatGPT 3 is 20 more times humans on Earth. So the number of parameters in ChatGPT 3 is like 20 times the population of humans on Earth. So then you see, well, of course, if you go to the class in, in calculus, probably second semester or second year, well, the professor said that every function, continuous function on a compact set of the Euclidean space has a minimum and a maximum. So what is the difficulty here? This is an Euclidean space, right? And the dimension, what was the dimension for the professor? Well, for the professor, the dimension was D. And what is the value of D? No, for the professor, we have very good professors. The dimension D is arbitrary. It doesn't matter. So the theorem of my professor applies there. So the global minimum exists. So if the question is about the existence of ChatGPT, this is not a problem. ChatGPT exists. There is an optimal choice of the coefficients, right, in which you can put into ChatGPT all the information that is in the Wikipedia. Of course, there are many technical issues, though, that you have to resolve. Because, as I said, in supervised learning, you need input and output. So when you take a web of the Wikipedia, a web page, one page in the Wikipedia, where is the input and where is the output? How do you organize all this information in a way that you have the X and the Y that you need in order to apply these ideas of least square employed in this large language, huge neural networks? It's not so obvious. There is a lot of engineering to be done in order to be able to fit the learning problem into this structure of, least squares a la Gauss and Legendre. Okay? Anyhow, you see, immediately you face the cost of dimensionality. But of course, you also have the devil of non-convexity. Even if you were able to manipulate this huge dimensional optimization problem in the computer, my claim is that this problem is non-convex. Yeah, because we also took a course in calculus operation, and the professor said that when the functional is convex, normally, gradient descent leads to the global minimizer, and if the functional furthermore is strictly convex, the global minimizer is unique. But do we have any chance that this problem is convex? Let's see. So here, of course, in least squares, everything is convex, right? This is a square. The sum of convex functions is convex. So this is linear, this is convex. So here, well, I see the same. I mean, I wrote here logs, but this could be just the Euclidean distance to the targets. This is just the penalization of the Euclidean norm of the coefficients. Everything is quadratic and convex here. So do you think the problem is going to be convex here or non-convex? A linear graph is linear, is represented by a matrix, is like Gauss and Legendre. Except, of course, because we are in several space dimensions, but also happens this to least square, right? So if X is in several space dimensions, then the beta will be a vector. This will be a scalar product. And if the X is multidimensional, of course, the betas will be matrices. So the problem of having matrices is already present in least squares. It's not only because I'm using neural networks. So then you think the problem is going to be convex? Well, something we learn in control theory is that precisely, even though for us it's very intuitive to employ bang-bang controls, like turn the lights on and off. This is what we do. Very rarely we turn on lights 70%. We just do on or off. Right? This choice of on or off is non-convex. What is convex is the segment joining 0 and 1. But the function which is obliged to take values 0 or 1, this is a non-convex operation. And therefore, the problem is not only facing the course of dimensionality, but the fact that this functional you are minimizing in order to train and compute the optimal coefficients is widely non-convex. So this will be a function with many, say, small wells, very far from the global minimizer, maybe interconnected by long plateaus, hills. So the landscape of this function in a space, a Boolean space of dimension 175 billion, is something that for us is simply something we cannot imagine. And therefore, it's not that easy, right, to find a global minimizer or even a local minimizer that is sufficiently deep to perform well. And this is why the training of these large language models is something that only the biggest companies can do, and for this they need to use plenty of resources, sometimes even too much, and there are of course many questions about the sustainability from the perspective of how much water we are burning every time we are training a large language model. Right? Very good. So I mentioned supervised learning. But now, if you look to the text and the books and the information on machine learning, sometimes you will see also references to unsupervised learning. And for me, as a mathematician, I was traumatized by it. Right? So, I mean, I can understand supervised learning. This is least squared. You give me input, output, a collection. Then I can try to fit this, and okay, we do it by neural networks if you wish, but this is just a minimization problem. Fine, that I understand. But some people claim we do unsupervised learning. And then you wonder, what can this be? So unsupervised learning means nobody gives you pairs of inputs and outputs. You don't have a training set. You don't have a priori information about, what are the radiographies with fracture and non-fracture. Of course, if you are educated as a traumatologist, you can decide. But if you don't have any clue, how do you do it? Will you just do it by the brilliance of the image, by the shape, the stereo shape? How do you do that? So actually, this is something that was already investigated in the 50s. And you can find very smart contributions. This GOID algorithm, I think it was developed maybe in the Bell laboratories in the 50s or so. So they were at that time already introducing some of the fundamental ideas that have been later wrapped up to develop this modern field of machine learning and artificial intelligence. This is what GOID did. Assume you give me I think the text is from the Wikipedia, and this video was done by one of our former PhD students, Martin Hernandez. He's now a postdoc in UCLA. So assume I give you this pavé, and I ask you decompose this pavé into 1, 2, 3, 4, 5, 6, 7, 8 regions. If I give you the exercise, please decompose the rectangle into 8 regions. Of course, the answer is not unique, right? You can take bands, vertical strip, horizontal strip. You can cut diagonally. You can just cut through, in equal sub-rectangles. There are many ways of doing it. You can just do random, say, polygons inside and leave the rest for the stereo domain. You just write 7 random polygons, and then the rest will be just allocated. There are many ways of doing it. But Joy thought, can I do it in a more structured manner? And he developed this dynamical system idea in which you combine 2 forces. And this is something you see often in machine learning strategies, right? So for a human, it's very hard to guess how do you have to maximize or minimize these giant models in billions of dimensions. We cannot figure out. But we can try to be smart and let the computer explore according to some rules that we have an intuition that this can be helpful for exploring this large dimensional universe, right? And this is what Lloyd said. If you ask me to split the rectangle into 8 pieces, I know there are many ways of doing it. But I will build an algorithm that once you initialize it, will lead to something which is deterministic, right? And then the James algorithm says the following. Start from an initial choice, arbitrary, of 8 capitals. So you place the 8 capitals wherever you wish, right? Okay? So you can do like in the map of Europe, where you have, in the north, you have a huge country because there was one capital, and the other capitals were farther away, and then in Central Europe you have many small countries because there were many capitals competing for the same space, but in the south you have bigger countries like Italy or Spain because there was only essentially one capital for every very distinguished regional area of the landscape of Europe. Anyhow, you initialize the process the way you like, you place 8 capitals. Once you place the 8 capitals, you say, oh, each capital should be the capital of a region. How do I determine the region corresponding to each capital? You say, well, I place in the region of each capital all points that are closer to this capital than to the others. And then you divide the domain into regions. But once you divide the domain into regions according to this criterion of distance, you realize that the capitals are not in the center. But capitals should be in the center so to better serve to all the citizens living in the corresponding region. So in this way you build an alternating model in which in one step you determine the contours of the region by proximity to the capitals, and in the next step you move the center according to the contours to be placed at the center of. And in this way you have an alternating dynamical system which, regardless how you start, it will rapidly stabilize and give you a splitting of the domain into 8 subdomains. Okay? So, well, what is the value of this? Well, frankly, without prior information, it's very hard to say, right? So it's like if someone tell me divide the group into 2 subgroups. Yeah, but according to which criteria? I can say left and right. I can say front and back. I can say glasses or non-glasses. I can say sleep or awake. I mean, there are many criteria. Right? But this doesn't have any value for any specific application. If the goal was to identify good PhD students, well, this is not a good thing, right? If it is about health or wealth or political opinion or soccer team favorites, no relevance. So then the question is, how do I make the problems I'm facing in artificial intelligence, in which very often I don't have this very easy scenario of Legendre and Gauss, input X and label Y, how can I make them look really more like a supervised learning and not an unsupervised learning problem, which is very nice, but probably out of this arbitrariness of the solution of the unsupervised learning problem, there is no generalization, no generativity, no knowledge I can claim, because it's so arbitrary. And one of the breakthroughs that is also explained in this web page was the next token prediction. I mean, this is very smart, it's very elementary, but it was also a revolution, right? So now I give you a page in Wikipedia, written in Italian, and I tell you, make a supervised learning problem out of it. to me is not that clear. Well, maybe if you give me this page in Italian and the same page in English, then I can see, oh, this is the X and this is the Y. And you give me many web pages in Italian and the same in English, then I have a collection of X's and Y's. Maybe I can build a supervised learning problem. No, but things are not that way. Things are more complicated. You have many web pages in different languages, many different contexts. Sometimes context can be also of multi-physics nature. Sometimes it's text, sometimes it's images, and you have to learn all this. How do you organize a well-structured supervised learning problem out of it? This was one of the breakthroughs. It was just next token prediction. So whenever you give me a text, a collection of words, because there is syntaxis and there is some coherence within the corresponding language in which it has been written, right? The next token can play the role of Y for the previous word or ensemble of words. And in this way, given a text, you can build the X and the Y. You take the first word, X, second word, Y. And then you take the first two words, X, and then the second word, Y. Of course, if you continue that way, it means that the dimension of the space of X's is growing and growing and growing. You have to limit. Then you will say, well, I will take just segments of, say, 10 words, and then the 11th will be, the next token will be the Y. And in this way, out of a data set of text, you can, which is structured already according to the rules, the syntactic and grammatical rules of the corresponding language, you can build a supervised learning exercise out of it. So this is to say that from a math perspective, it's very easy to oversimplify what machine learning is doing. In practice, there is a lot of very smart engineering that has been developed in order to build this effective. The same will apply, of course, when you look to the to the Nobel Prize awarded for the protein unfolding, right? So probably mathematically the ideas are not very far from using neural networks just to train and discover, new configuration. But there is a lot of, say, scientific intelligence employed in order to be able to transform this very complicated problem in chemistry into one that is tractable using these more or less elementary mathematical ideas. Okay? In any case, this has been a revolution, and the world has changed. Right? So until now, mathematics was, for us, applied mathematics was about basically partial differential equations, right? Because according to mechanics, whenever you are telling me about a problem, if you tell me about an airplane, well, I know the airplane is flying on air, and then air is a fluid. Oh, then I have the equations of Euler or Navier-Stokes. If you are thinking on heat on a building, then I have the heat equation. But if I'm thinking on diffusion models for population dynamics, also it will be like a nonlinear heat equation. So KPP, Kolmogorov again, K for Kolmogorov in population dynamics. The static version will be the Laplace equation. If you are dealing with flexible structures like strings or drums or 3D elasticity, and our bodies are elastic, so we are all the time vibrating. This can be modeled through wave-like equations, acoustic waves, sea waves, tornadoes, wave equation. Until now, everything was based on modeling through mechanics and partial differential equations. But suddenly, there is this tsunami of artificial intelligence arriving, in which you don't need PDs anymore, right? And maybe you can use some ideas of PDs, why not? And this is something we should try. But in principle, it's true that when you are dealing with text translation from Italian to English, this doesn't seem to be a clear problem fitting the classical classification of models in mechanics, according to which I should say this is elliptic, this is parabolic, or this is hyperbolic. Right? So then there is a new need of new mathematics and new modeling paradigms, and neural network modeling using these ideas of training through supervised learning has become so popular because its capacity of adapting to any scenario. Unlike PDEs that, well, of course, PDE are adaptive as well, right? Because if you say that, our bodies, I said, are elastic, but they are not elastic. Actually, they are thermoelastic, right? Because depending, and this is why when you are going to exercise, it's better to heat first, because when you heat, you are increasing the elasticity coefficients, right? So the Lamé coefficients of your muscles change. Our bodies are thermoelastic. So if we talk about thermoelasticity, we can figure out that out of the heat equation and the weight equation, I can cook a system coupling elastic components and deformations and temperature and build a system of partial differential equations called thermoelasticity. I can also do viscoelasticity or viscothermoelasticity. So mechanics can get quite far, but never to the point of being able to adapt to any scenario in which you have to learn about anything and hopefully do it in real time. So for instance, to anticipate how many people will be attending the next marathon in Padua. When is the next marathon in Padua? June. How many people will come? Well, is this what? Is this elliptic, parabolic, or hyperbolic question? Very hard to say. But certainly it's a question that is very well adapted to be tackled using this kind of ideas. Okay? Of course, the problem is not that easy, right? Because you can build a table, say year per year, and how many attendees there were. But maybe the number of attendees doesn't only depend on the year, but it depends on the weather, it depends on the economy, it depends on whether, there have been some major, say, air traffic problems in the days before, and so on, right? Okay. Anyhow, these kind of challenges of modern society seem to be more adapted to be tackled through these new ideas in machine learning. Actually, all ideas, but implemented in a modern and very sophisticated manner nowadays, than to classical mechanics. Now, of course, when you, for instance, compare ChatGPT and DeepSeek, they will tell you, listen, if DeepSeek succeeded to do what ChatGPT was doing with less computing, it was because there were more people post-processing, right? So, because in this context, you also observe that ChatGPT is learning, right? So, some questions that were wrongly answered maybe in the beginning of the year, when you ask now, they are, they have the right answer. Why? Because it's not only that you minimize and compute the coefficients 1, but there is plenty of everyday human interaction in a way that is reminiscent with from classical reinforcement learning, that, as you know, is a natural derivation of this challenge that Bellman already anticipated, right? So reinforcement learning is, to realize that what Bellman said is a barrier that you cannot overcome. If you have to control a large dimensional system, the truth is encoded in the solution of a Hamilton-Jacobi equation in very high dimension that you cannot solve. And therefore, the best you can do is try to learn how to approximate this solution, but in a smart way, learning from experience. And this is what reinforcement learning does. And it's actually mimicking what we humans do, right? For instance, if you are offered a new computer, assume you are offered for Christmas a new computer, the new computer comes with a 500 pages book of instructions for users. What do you do? of course, you open the book and you read the 500 pages, isn't it? No, nobody does this. What do? You immediately open the box, you turn on the computer and start operating. And then you discover, oh, you know, it seems to be faster. Oh, but now, you know, the PPT tool is better, right? Oh, and the PPT tool is connected to artificial intelligence, to some of these large language models, so that when I am preparing my slides, I don't even need to go to the Google to search for images, but I just click, you know, on the slide I click image of bridge in Padua, and I immediately get the photo downloaded by the computer without doing anything. Well, of course I need wireless connection. That's all. So we learn by doing. And the more we use the computer, the more we learn, the better we use it, and the more performant we become. This is one of the keys that has been implemented in DeepSeek. Other ideas that have been implemented in DeepSeek and are very much rooted in classical applied mathematics is not learn everything in one shot, but learn in an iterative manner, in a multi-scale manner. And this is also one of the classical principles of numerical mathematics, right? So you don't need to compute the whole system in one shot, right? So you don't need to restore, right, the structure of this building in the finest, right, grid, right? Probably you can design the shape of the building in a very coarse grid, but then when determining the rugosity of the walls, right, maybe you need a finer grid, right, to determine whether, you know, the materials you are employing, you know, there is this granular painting or the painting is simply fine. So you encounter many of the classical ideas of control theory and classical applied math employed in this modern large language models. Okay? And of course, when you look to how engineers and computer scientists develop these devices, there is also, of course, a lot of statistics, right? So, of course, for us, you know, as an applied mathematician, I expect someone will give me the data set, right? I expect someone will come with the, you know, with the chariot full of data, X input and Y output. But there is, of course, a lot to be done from the point of view of statistics in whatever process you are considering, in order to make sure that you have a data set that is sufficiently good, but not too large, right? So the key of success is having a data set that represents the complexity of the landscape or the process you are aiming to learn, right? Without providing you too much information that is redundant, because whenever you have one more data, this adds one more term on the sum. And recall that you have to train this loss function. Training means apply gradient descent in a way or another. And applying gradient descent means in every step you have to compute all the partial derivatives. And there are 180 billion, right, variables. So every gradient is 180 billion partial derivatives. So how many billions of the partial derivatives that a student, a regular student in Padua compute in one weekend? How many billions do you do? Maybe many, but not 180 is a lot, right? But not only you have to do 180 billion partial derivatives in each step, but the partial derivatives have to be taken on the sum. And the sum from 1 to n, capital N, is the number of data. So the more data you add, the more complex the loss function is, and the more partial derivative you have to compute. So, you know, there is a lot of statistics to represent the reality you are aiming to model well, but without adding too many data, because this increases the computational problem. Okay. So let us now talk about the mathematical principles. So the first lesson is the beta one, the beta lesson. This is a a lesson. Shelton also is one of the popes in this field. I think he got one of his big prizes, the Tulip Prize or so. So basically what Shelton said the following. He said, well, after working in this field so many years, I realized with frustration that our efforts were not that fruitful. In the sense that there is not so much you can do from a mathematical perspective. The best you can do from a mathematical perspective is just to make sure that you provide to the computer a model that is sufficiently rich so that the computer can compute. Actually, for us as applied mathematicians, this is not so surprising. This is like saying, listen, you can learn all the functional analysis you want, all the PDE theory you want, all the numerical analysis you want. But in practice, when you have to solve or even control, right? You can study as much control theory you want. But then when you are given a dynamical system and you have to actually compute the numerical value of the optimal control, this is not something you can do yourself. The only thing you can do is make sure you have let the computer employ algorithms that you know are sufficiently good so that you can get a good approximation of the controls, provided you have sufficient computing power, energy, and time. And this is what Shelton says. So don't expect that nobody will tell you how these gadgets learn the Wikipedia. No. The only thing we can claim is that we were able to build sufficiently large neural networks with sufficient, say, transitions inside. And we were able to combine sufficiently, well, all these ideas of next token prediction, statistics, and so on, so that once this is, delivered to the computer can function. And actually, one of the big issues nowadays in artificial intelligence is interpretability. And this is going to become even a more and more important problem in the future. Because of course, yes, so nearly everything can be done using large language models. Yes, but are we sure that we use large language models in order to allocate, fellowships to the students? There is not some, within the data set of the algorithm, there is not a deviation that is favorizing some students instead of others. Are we sure that this is equal opportunity, right? How do we guarantee this? Of course, this is not guaranteed by humans either, right? Because, we as teachers, as professors, we allocate marks. If you ask to a professor, can you describe step by step all the ingredients you have taken into account in order to say that this exam is 7,2 and this one is 6,8? Probably not. So it's very hard to undo, right? Even ourselves, when we make a decision, it will be very hard for us to explain what was the thinking process we have elaborated step by step to come to this decision, the same here, right? But because these tools will be more and more used for relevant, say, applications, like for instance, allocating public resources or justice, we need to understand them better, right? And this will be one of the challenges. Why? Because as Shelton explains there in the later lesson, we didn't actually do it. We just let the machine compute simply because we cannot understand a word of dimension 180 billion. Impossible. No hope. Okay? Interpretability of machine learning is therefore kind of an inverse problem, right? Mathematically speaking, this will be like an inverse problem. Right? You came to a decision, right? You are right, but the question is how you do it. How you did it. Very good. Okay, but now trying to go to the fundamentals. Probably the first result that we should mention in this context is about universal approximation theorem. The universal approximation theory in machine learning is what in analysis we know as density. We all know what density it is, right? So we know rationals are dense, irrationals are also dense on the real world, right? We know that, for instance, say-infinitely and compactly supported functions are dense in nearly all spaces, right? LP spaces, Solev spaces. Of course, they are not dense in an infinity because, right, the uniform limit of continuous functions is always continuous. You have to be careful about some extreme cases like L infinity, but otherwise, say infinity and compactly supported functions are dense. Fourier series. We know that Fourier series, you have for instance, an orthogonal basis of L2 made of eigenfunctions of the Laplacian. So finite linear combination of eigenfunctions are dense in L2, or in the Solev space A10. What other examples we know? Oh, we know Stone-by-Strass, right? Polynomials are dense as well. So all this is known. So this is a new category of density results, and probably the first one to mention in this category is the one by Norbert Wiener, Tobelian theorems, back in 1932. He wrote a 100 pages article in Annals of Mathematics, very much devoted to Fourier analysis, right? By Wiener, okay, it was the time, by the 30s, where many of these contributions were being done. He said the following. He said, give me a Gaussian in multi-D, so here the drawing is in 1D, but X can be in any Euclidean space, RD, as we analyze like, and we don't care whether D is 2 or 180 billion, doesn't matter. Give me the Euclidean space of dimension D, give me a Gaussian function. You fix it. You take a G with a given center and a given variance. You give me a G, a Gaussian function, a Gaussian bed. And then I claim the following. If you want to approximate any function, doesn't really matter, so any function, say in L2, and you give me an epsilon, I can always find the number of neurons that I need. I will call this to be, each of the terms in this series will now be, in this approximation answer, in this approximation formula, will be a neuron. I can determine how many neurons I need so that the combination here is epsilon close to F. For this, I need, of course, the number of terms to be large, but this is typical. This is when I say also that polynomials are dense, yes, but are dense, but if you want to approximate a very wide function, you need a polynomial of a huge degree, right? So the same here. So K has to be large, and once K has been fixed, you need to choose the centers of gravity, B, of these Gaussians, minus B are the centers of gravity of these Gaussians, and the heights, you have to choose them properly. This is a dense set. This is this way. Okay. So basically what it means, when you look to the hills over there, I immediately can see the peaks, and therefore I will place the Gaussians according to the heights of the peaks located on, the center of gravity of these peaks, and in this way, if I combine sufficiently many peaks with sufficiently many centers and height, this is dense. The proof of Wiener uses the Fourier transform. Right. And in the proof, he claims I need this Gaussian. Actually, his proof doesn't only apply to the Gaussian. The proof of Wiener applies to any, say, atom like this, under the condition that the Fourier transform of this atom never vanishes. And what is the best example of function whose Fourier transform never vanishes? Well, it's the Gaussian, because the Fourier transform of the Gaussian is the Gaussian, right? And therefore, so I think if I am not wrong, just thinking on the fundamental solution of the heat equation, I think that is 4 pi minus d over 2 exponential minus modulus squared over 4. in dimension RD, the Fourier transform is always exponential minus modulus C squared. In any case, the Fourier transform of the Gaussian, well, of course, it depends also on how you normalize the constant in the definitions of the Fourier transform. But the Fourier transform of the Gaussian is a constant, therefore is never zero. And you see that this will appear immediately in the proof, because if you, let's do the proof mentally. You take here the Fourier transform of the left, f hat, and the Fourier transform of the right. Of course, the Fourier transform of the sum is the sum of the Fourier transform, W are coefficients, and then you take the Fourier transform of this. What is this? Oh, a shift in the Fourier transform is a change of phase. So you get the Fourier transform of G multiplied by a phase exponential I C multiplied by Bj. But if the Fourier transform of G is non-zero as it is, you can divide and you put everything on the left-hand side, and you are just doing the Fourier transform, a Fourier, discrete Fourier approximation of the function on the left-hand side. That was his idea. So in 32, Wiener says, if you have an atom as a fundamental element whose Fourier transform is never zero, by translation and amplitude regulation, combining them, you can approximate any function. So this was the starting point of a whole new field. It's the field of nonlinear approximation theory. Until then, everything was Fourier, Stone-Weierstrass. These are linear approximation paradigms. This is nonlinear. Why? So think, for instance, on Gauss and Legendre. Gauss and Legendre said beta 0 plus beta 1 times x. Beta 0 and beta 1 enter in this formula linearly. But here, this is a nonlinear ansatz. Why? Because B enters nonlinearly within the argument of the Gaussian. So now, even if this is true, even when you know analytically that this is true, if I ask you, okay, fine, but now, right, you know that you have an analytical proof, but now I wanted to make it computational. So given K, so K given, please minimize this L2 distance with respect to the coefficients Wj and Bj. This problem is non-convex. Right? Why is non-convex? It's the same reason as before. Everything looks quadratic and nice, yes, but the dependence of G on B is very nonlinear, and therefore this problem is non-convex. So even in low dimensions, if I just plug this functionally in my computer and apply gradient descent, I have the risk that the iterative algorithm will be trapped on some local minimizer without ever getting to really the global one. So you see that here there is also a very huge computational challenge. The fact that you know that given an epsilon for K large, there are W and B that are epsilon close to the target, it doesn't mean you know how to find them. You know there are, but this doesn't help. You need to find them. And this is a non-convex minimization problem. Okay, so the impact of moving from linear approximation theory to nonlinear was, in nonlinear you can do many more things. Right? Yes, but to the price of dealing with non-convex optimization problems, we're trying to, actually get the best. While in linear approximation theory, each coefficient is very simple, it's just a scalar product, these Euclidean projections. In linear approximation theory, you just compute every coefficient, by just doing scalar products. Here, the nonlinear approximation theory, it looks like a subtle change. No, it's dramatic because when you try to actually compute the true coefficient, this becomes very, very difficult. It's an uncomplex problem. Actually, you see that in these problems, there is a lot of underdetermination. So you see, they call it universal approximation theory. They say this is dense. I would say, actually, it is not dense, it's super dense. Actually, my claim is there are many different ways of approximating a function f in this way. Why? Because basically you could choose first the center B a priori in a random manner, choose the centers. The likeliness that these functions will be linearly independent is very high, because basically you will only lose the linear independence of the translated Gaussians when two centers, end up at the same point. Otherwise, as functions, they are linearly independent in L2, and therefore they generate a basis, and therefore you can define the corresponding W's which better approximate the F. So not only given an F, there is not only, or given an F or given an epsilon, there is not only one way of approximating the function F through these answers, there are many, many ways. But this is good or bad? What happens when you get to a restaurant and then they give you the menu, right? And the menu has like 30 pages. So finally, you finally wait until the waiter comes, and then you ask him, "Well, do you have a recommendation?" Right? Just tell me one or two things, and then you choose the one that sounds more. Right? You don't want 30 pages of menu. The same here. The fact that there are so many different minimizers, so many candidates, makes the problem hard. Because basically each of them is contributing to a global minimizer or a nearly global minimizer, so it will make the search problem much more complicated. Of course, it's much easier to find when you have one single dish in the menu. You go to the restaurant, there is only one dish, and they ask, "What do you want?" And you say, "What do you have?" "Well, we only have, this dish." "Okay, we'll give you this one." Or a glass of water. I mean, you have two choices. Eat or not eat. So this is the case of convex function. We are very far from this. Okay, so Wiener did that for some reason, and the topic was forgotten. It took 57 years until Sivenko publishes this paper in a control journal that actually, this is the second volume, so it was inaugurated that year. At that time, I think it was founded by Sontag and Willens, probably, if I'm not wrong, but I'm not sure. But these were, basically people descending more or less directly from Kalman. And then what Sivenko said, he said, "I can do the same as Wiener, but slightly different. I can replace the Gaussian by a sigmoid function. A sigmoid function is just a continuous function taking value 0 in one side and 1 in the other. It's just like a traveling wave front, like in here. So give me any sigma which is continuous and has 0 limit on the left and 1 limit to the right. And then let me cook combinations of this sigma, and I am done." People said, "This is very exciting because this really looks like, neurons, right? Now this sigma is really mimicking the behavior of neurons being off whenever sigma is close to 0, or being on whenever sigma is close to 1. And actually this function sigma, contrary to the Gaussian, because you see the Gaussian here is plotted in 1D, as I said, if we are in multi-D, the Gaussian has to be multi-D. This sigma is always 1D, independent of the dimension in which I am. Actually, to make this f, which depends on x, to be approximated by these ansatz, I need to use coefficients a, which are vector value. So the coefficients A are vectors now. And then A dot x means a scalar product. If you compute here, how many coefficients do you have in each neuron? So here you have D coefficients for the center of gravity in RD, and 1 for the amplitudes. Here you have D plus 1, while here I have D for A, 1 for B, and 1 for the amplitude. So you have D plus B. But the advantage being that this sigma is just a 1D function. Nowadays, people prefer, instead of using the sigmoid, very often they take this function, which is even simpler, is 0 to the left, linear to the right. This is what is called the rectified linear unit, and this is the typical function we use all the time in PDs, for instance, to prove the maximum principle for elliptical parabolic equation. It's just the positive part of the function that we use as test function very often for, typical calculus of variation and monotonic elliptic or parabolic equations. Okay? But this is a nonlinear ansatz as well. As I said before, the ansatz of Wiener was nonlinear on the D parameters of the center of gravity D. The ansatz of Sivenko is nonlinear on the D plus 1 parameters of A and B. Now actually, for instance, when you think on this rectified linear unit, you realize that sigma is either 0 or nonlinear, and then this allows you, for instance, to normalize the vector A to be 1, so that eventually, to the price of taking A to be in the sphere, in the unit sphere, you can also make the number of free parameters here to be D plus 1. Okay? But I will not enter in this counting. In any case, if you are dealing with very complex, high-dimensional problems, and you see that dimensions grow very fast when we are dealing with data, right? So, for instance, you take when you go to do a blood test in the doctor, how many parameters do they measure? I don't remember, but probably there are what, maybe 40 parameters. Well, there are plenty of numbers, right? I don't know. I mean, there are different dozens of them. So you see, you are immediately just to classify outputs of analytics of data, blood analysis of standard clinics. You are in a Euclidean space of dimension several dozens. So whether this is D plus 2 or D plus 1 is not such a big deal. Okay? But certainly, this was the starting point of one of the ignition, say, elements of this artificial intelligence career was the fact that people recognize, oh, this really looks like neurons, so we call this a neural network, right? So here, where do you see this network structure? So here you don't see this network structure. Basically, what you see here is a very tall column, right? But you see, when I was mentioning before that you have many choices for the architecture here, of course, nothing excluded that all the neurons will be piled up on a very, very, very tall column. Now, what happens typically to tall columns? Well, I mean, they are hard to make stable, they are hard to manipulate, so assume, in this very tall pile of neurons, somebody says, no, but I would like to modify the neuron number 2 here. You say, be careful, if you touch number 2, maybe the whole column will fall. But that was the starting point. It was very shallow neural network, shallow to the point that there was only one layer, and the layer was very tall. Because there were so many neurons piled up, as capital K indicates, typically large, to approximate. Now, what was later done was, little by little, make this neural network ansatz of Sivenko and Wiener evolve, and to say, well, what if instead of piling up all the neurons in one shot in a very, very tall yellow column here, we gradually, organize them in a deeper manner, so that we try to learn gradually. Learning gradually with different layers probably is also helpful, right? Because as we have said, this is something that has been implemented in DeepSeek, this idea of multi-scale learning, the same as we humans see, right? So we first see the building, and then we recognize, oh, there seems to be someone in that room, because I have observed a shadow moving. But I mean, I don't observe that in the first watch. I first see the building, then I realize there is one light in that room, and when I am watched more precisely, I can indeed observe human motion. There is someone later in that later room. Okay? So these ideas of multi-scale learning, of interpretability, of making things more understandable and more manageable for human minds led to replace these static answers of Sivenko and Wiener into something more dynamic, at least from a time discrete perspective. Okay? Yeah. I conclude with this. This is the point where I wanted to get today. Once you are there, you realize, oh, but this is something we know already. This is actually what classical control theory has done. Right? So we can start tomorrow by this, but you probably all know. This was one of the breakthroughs. I mean, I think this theorem is attributed to Kalman. There are, at that time in the 50s, there were many people, probably also here in Italy, right, doing similar things, Lyapunov and so on. Probably Kalman was the one who wrote this more in a cleaner manner, very much also inspired by, you know, the classical formulation of Cauchy, of a Cauchy problem, or Hadamard closeness for evolution problem. He said, listen, this is the kind of system we should look at. There is a clear concept of controllability, and controllability is something that can be characterized in algebraic manner. Okay? And this will be the starting point of our lecture tomorrow, in which we will deploy this control theoretical interpretation of machine learning. Okay? Thank you for your attention. Thank you.